Welcome to the video lecture series for Texas A&M University course Math 152. Today we will take a look at section 10.7, Taylor and Maclaurin Series. You can find the accompanying handout at bit.ly/Raelene Math 152. Let's begin. In this foxtrot cartoon, the girl asks, "I keep forgetting, what's the cosine of 60 degrees?" Her brother, Jason, the math nerd, says, "Well, let's see. If I recall correctly, 1 minus pi by 3 all squared over 2 factorial plus pi by 3 all to the 4 over 4 factorial minus pi by 3 to the 6 all over 6 factorial, etc., etc." And as the paying sister for the math tutoring, she says, "In case you've forgotten, I'm not paying you by the hour." 1/2. So according to the cartoon, state two different ways that do not involve cosine to give cos of pi by 3. Well, we know simply the cosine of pi by 3 is 1/2. So cosine of pi by 3 equals 1/2. But there's another representation given. It is an infinite series. 1 minus pi by 3 all squared over 2 factorial plus pi by 3 to the 4, cubed all to the 4 divided by 4 factorial minus pi by 3 cubed, pi by 3 to the 6 over 6 factorial plus pi by 3 to the exponent 8. I keep saying something different from what I want to write. Pi by 3 to the exponent of 8 over 8 factorial, etc. And we can actually find this as a pattern. We can see that we have the nth general term, where n is going from 0 to infinity. We have an alternating series, so we have -1 to some expression. We have pi by to some exponent. We have pi by 3 to an even exponent. So what I'm going to do is take this to be n equals 0, then n equals 1, n equals 2, n equals 3, n equals 4. And we can start to see what is changing every time. And we can make a relationship between the number in the green circle and the red value for n. We can also express the first term using the same patterning. And we can write it as 1 times pi by 3 to the exponent of 0 divided by 0 factorial. And now we can see that all of the green circled numbers can follow the same pattern. Namely, the exponent is going to be 2 times n, 1 pi by 3, and the denominator is going to be 2n factorial. But we still need to deal with the fact that we have an alternating series, and so we have positive first and then negative, positive, negative, etc. And so we know that whenever n is an even number, the output sign is a positive. So we can simply write -1 to the exponent of n times pi by 3 to the 2n all over 2n factorial. So we have 1 and 2 different ways to express the cosine of pi by 3. In number 2, we want to write a power series expansion for 1 over 1 plus 4x to the 4 and state the interval of convergence and the radius of convergence. Well, if we go back to the sum of a convergent geometric series, we can see that the a value is equal to 1 and the value for r is equal to -4x to the 4. So if we start off with our basic f of x, which is 1 over 1 minus x, and we have 1 plus x squared plus x cubed plus x to the 4, etc., plus x to the n plus ... Then we can say that f of -4x to the 4 is going to give us the same thing. If we had had a different value for a, for example, some function g of x, then we would have had to multiply by g of x as well. But we don't have a equal to g of x. So we have a is equal to 1, so we're multiplying by 1 here for the value of a. And so we get 1 over 1 minus -4x to the 4 in brackets, which is of course 1 over 1 plus 4x to the 4. And we get 1 plus -4x to the 4 plus -4x to the 4 all squared plus ... plus -4x to the 4 all to the n plus ... And so if we want to state the interval of convergence, we can come up with the expression for r, knowing that r has to be contained between -1 and 1. It may be practical for us to come up with the sigma notation for this, so let's do that for the given function. And we're going to have n equals 0, n equals 1, n equals 2, etc. n equals n over here. And so we're going to get from n equals 0 to infinity, we are going to get -4 to the times x to the 4, all to the exponent n, which we can express by separating the alternating part, -1 to the n, and then 4 to the n, and then x to the 4n. And so then if we want the interval of convergence, we first of all need to solve for x. So we have that -1 is less than -4x to the 4, which is less than 1. And if we think graphically here, we're going to have the graph -4x to the 4 looks something like this. And we're going to have a horizontal line at y equals -1 and a horizontal line at y equals 1. And we can find the intersection points for the red curve and the blue curve by solving for the intersection points. We solve an equation. And so the intersection points will be solved by 1 is equal to 4x to the 4, so that x to the 4 is equal to 1/4, which means that x squared is equal to plus or minus 1/2, which means that x is going to equal plus or minus the square root of positive 1/2, or plus or minus the square root of negative 1/2. And we are going to have, these ones are non-real, and therefore extraneous. Well, not really extraneous, just not real. And so we're going to get two solutions of -1 over root 2, or positive 1 over root 2. And so the interval of convergence is going to be between those 2 points, and we need to test the endpoints as well. So testing the endpoints, we will test x equals -1 over root 2 first, and the series becomes, let's just see from here, when we substitute x to the 1, x is 1 over root 2 here, we get raising to the 4 gives us 1 over 4 back again. And so we're going to get, better if we plug it in here, 1 over 4 times -4 is -1. So when we substitute, in fact, it doesn't matter if we substitute plus or minus 1 over root 2 in. So since it doesn't matter which one we substitute in, the series is going to equal the series from n equals 0 to infinity of -1 to the exponent n. And this is going to be a series 1 minus 1 plus 1 minus 1 plus ... But since we know that an does not approach one constant height or value as n approaches infinity, we have that the limit does not exist, and therefore the series is not convergent. And so we do not include x at the endpoints. And so our interval of convergence is going to be from -1 over root 2 to +1 over root 2. And thinking of that as the interval with 0 at the center, we can see that the radius of the interval, or the radius of convergence, is simply 1 over root 2. Number 3 asks to explain whether the following statements are true or false. Part A asks or states that the product of a geometric power series with another function is also a geometric power series. F of x can have a geometric power series of the form a over 1 minus r, and therefore a function f of x multiplied by another function g of x. And when we talk about this other function, we just mean a finite number of terms. Then we have a times g of x all over 1 minus r. And so what we're having is a new a, or start term, and the power series for f of x, the power series is a times g of x. But we notice that the common ratio of r hasn't changed. And since the common ratio hasn't changed, we have that f times g is a geometric power series. So this is true. In part B, it says the composition of a geometric power series is also a geometric power series. So again, if we start off with f of x equals a over 1 minus r, and therefore f of g of x is going to be a over 1 minus g of x, we have that the series could be expanded as, I'll move it down here. This series could be expanded as follows: a plus a times g of x plus a times g of x all squared plus dot dot dot. And so since we have the common ratio is equal to g of x, we still have a geometric power series. And so this one is true. In part C, it says that the derivative or antiderivative of a geometric power series is also a geometric power series. Well, keeping in mind that the derivative of x to the n is equal to n times x to the n minus 1, this tells us that the derivative of x cubed is going to equal 3 times x squared, and the derivative of x4, for example, is 4 times x cubed. And so it's going to be very difficult to have a common ratio when we have coefficients of n in front of each term in a derivative. So we can take a look at a general power series. As an example, let's look at 1 over 1 minus x, which is 1 plus x squared plus x cubed plus dot 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 plus x to the n plus dot dot dot. And then we know that the derivative of that power series can be still another power series for 1 over 1 minus x quantity squared, but the derivative is going to be 1 plus 2x plus 3x squared plus dot 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 plus n times x to the n minus 1 plus dot dot dot. And so while we still have a power series in x, because we don't have the constants being common, or rather the coefficients being constant, we have changing or variable coefficients, therefore we do not have a geometric power series. So because C0 does not equal C1, does not equal C2, does not equal dot 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 Cn, therefore no common ratio, therefore not geometric power series. And so our answer is false. I've only shown the example here, or the counterexample, for derivatives, but of course antiderivatives has the inverse type of behavior. The antiderivative of x to the n is x to the n plus 1 divided by n plus 1, and as a result, the antiderivative will not be a geometric power series either. In number 4, we are asked to determine the equation of a parabola that passes through the 3 points. What we know here for a parabola is that we're starting off with a model, y equals ax squared plus bx plus c, and we want to solve for the 3 parameters a, b, and c. So we have 3 unknowns, a, b, and c, which require 3 equations. And what we have here are 3 different sets of x, y ordered pairs. For each pair x, y, we can make an equation. I'm going to pause the video, you pause it, try it yourself, and I won't go through the steps of doing this to save time in the video, but I will have the answers here when you resume the video. Good luck. Coefficients to be a equals -1, b b equals to 2 and c equal to 4. And we can plot the equation of the parabola, and we can confirm that those 3 points do in fact pass through this parabola. The point of this question is to show that when we have some unknowns, we need as many equations or pieces of information as unknowns to solve for them uniquely. We will see a different way of solving that doesn't just require having x and y information, but maybe other things about x and y. For example, if we look at a parabola, we could associate a tangent slope with each point. And the slope of each tangent would be given by the first derivative. So we could talk about ordered triples. We could also talk about the concavity, the amount of curvature of the parabola or the curve at that x-coordinate, and so we could introduce a second derivative. These have been referred to before as ordered quadruples, but there's nothing to stop us from saying, let's talk about the third derivative, the fourth derivative, and the fifth derivative associated with this curve, y equals f of x, at a particular x-coordinate. And so we can extend this idea later on when we talk about Taylor series. In number 5, we are asked what are the 6th, 7th, and 8th derivatives of a 7th degree polynomial. Well, if we started taking a look at some of the derivatives, the first derivative is going to make the first term 0 because it's constant, and so we will get c1 plus 2c2 times x plus dot 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 plus 6c6 x to the 5 plus 7c7 x to the 6. Derivative would work out to be 2c2 plus, well, this next term would have been 3c3x squared, so now we're going to get 3 times 2c3x plus dot 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 plus 6 times 5c6 x to the 4 plus 7 times 6 c7 x to the 5. So we're going to need to take a few more derivatives until we get down to the 6th, 7th, and 8th. So maybe with a bit of patterning we can see what they will be. We can see that the first derivative left us with the linear term being constant, and so the second derivative made that linear term have a 0 in its space. And so when we wanted to take the derivative of a quadratic, the first derivative that will be 0 is the third derivative. And therefore, when we take the derivative of a 7th degree polynomial, the first derivative that will be 0 is the 8th derivative. The derivative before that will be constant, and the derivative before that will be linear. And so we really need to focus on these last two terms. When we take the derivative so that we get a constant, we've taken the derivative until we get down to x to the 0, which means that we will have 7 times 6 times 5 times 4 times 3 times 2 times 1, and then the exponent will be 0, which is the 1 less than the last coefficient. But this is nothing more than 7 factorial, which means that the antiderivative of that, actually let's not forget that we had c7 in here. And so the antiderivative of 7 factorial c7 is 7 factorial c7 times x to the 1 divided by 1. But then we also have to have a c6 term that is constant. And so the c6 term is going to be 6 times 5 times 4 times 3 times 2 times 1 times c6 times x to the 0. And so we see that we're getting 6 factorial c6 plus 7 factorial c7x for the p6, or the 6th derivative of p. That's a bit crowded. Let me rewrite it a little bit more neatly. Okay, we're going to need this later on when we generalize the result. In number 6, we want to construct a 4th degree polynomial given as follows, which means we want to determine the coefficients. So this sounds very much like the question number 4 that we saw with the quadratic equation given 3 points. The difference is that we are given one x value of 0 as opposed to a number 4 where we were given 3 different x values. So how are we going to come up with enough pieces of information to solve for the 5 coefficients? Well, we're not given 5 different x, y ordered pairs. Instead, we're given ordered quadruples. Or rather not quadruples, quintuples. We're given x, y prime, y double prime, all the way up to the 4th derivative. And so we are coming up with 0, 1. The 0th derivative is the original height. And then 2, 3, 4, 5. And so we are going to take these pairs of numbers one at a time to solve. So we have that p of x is given as c0 plus c1x plus c2x squared, etc. And we can use the information about x, y to solve. In other words, we know that p of 0 is going to equal to 1. We're given that. And we know that substituting 0 in for the polynomial gives us only c0 left. So we can solve for c0. I'm going to do the second one, then turn off the video, and you can check all of the rest of the solving beyond that. The next thing we need to do then is come up with an equation that allows us to substitute into p prime. So we need the first derivative of p at x, which is going to be c1 plus 2c2 times x plus 3c3 times x squared plus, that should be x to the 4, plus 4c4 x to the 3. Now, given that we know we are substituting x equal to 0, once we hit this term, we didn't really need to write these terms, so we could have just put plus ... terms involving or terms in x. And so when we do this, we see that p prime of 0 was given to be 2, and therefore p prime of 0 leaves only the c1, and so therefore c1 is equal to 2. Okay, so try solving for c3 and c4, c2, c3, and c4, and I'll pause the video for now. For c0 through c4, and there's a little bit of patterning that shows up. We have the given constants, or values, 1, 2, 3, 4, 5, which were the derivative values, divided by 0 factorial, 1 factorial, 2 factorial, 3 factorial, and 4 factorial. We'll keep this in mind when we're going later on in the lecture. Okay, in number 7, we are given the graphs of f of x, which is 1 over 1 minus x, and then some polynomials. Let's label the graphs with its function letter. Well, we see that f of x has a vertical asymptote at x equal to 1, and so that is the blue graph. And then g of x is the constant function, which is the purple line, y equals 1. H of x is the linear function, which is in red, 1 plus x. K of x is the quadratic function, concave up with no x-intercepts. And m of x is the cubic polynomial, which is in turquoise. And so there is the function m. Okay, so on what domain do the polynomials approximate the rational function? We see that the polynomials seem to look like they are matching the rational function in around here. It's not really obvious what it is, but we think somewhere between, on either side of 0, maybe negative 1 to 1 looks reasonable. We know that we won't include x equal to 1, as that's not even part of the domain of the function f. Now on the next page we have a table, and we will fill in the table. Completing the table, let's work out the first, second, and third derivative for each of these, and then evaluate the values at x equals 0. So the first derivative of f of x is 1 over 1 minus x all squared. It's going to be negative 1 and then times a negative 1 from the chain rule. The second derivative is going to be negative 2 times 1 minus x to the negative 3, all times negative 1. So it will be 2 over 1 minus x to the 3. And then when we take the derivative the third time, we're going to get 2 times negative 3, and then times negative 1 from the chain rule. So it's going to be 6 over 1 minus x to the exponent 4. The first, second, and third derivatives of g of x are easy. And for h of x, we have 1, and then we have 0, 0. And I'm going to put these 0, identically equal to 0 derivatives in red. We know that the third derivative of the quadratic will be 0, and the third derivative of the cubic will be constant. So I won't put any more zeros in. The first derivative of k of x is going to be 2x plus 1, and the second derivative is 2. Meanwhile, for the cubic, we get 3x squared plus 2x plus 1, and then we get 6x plus 2, and then we get 6. So we're going to be focusing on the non-zero functions and their derivatives evaluated at x equal to 0. So when x is equal to 0, we notice that each of these functions, f, g, h, k, and m, f equals g equals h equals k equal to m, and we get that f of 0 is equal to 0. In the second column, for the first derivative, we see that when x is 0, f prime of 0 is 1 over 1 squared, which is 1, and so will the h prime, k prime, and m prime. So we have f prime equals h prime equal to k prime equal to m prime, which is a value of 1. And we see that f double prime, k double prime, and m double prime at 0 are all equal to 2. And lastly, we see that at x equal to 0, f triple prime and m triple prime are the same, and that value at 0 is equal to 6. So we could think of it as an ordered quadruple, if you like. We have, rather quintuple, we have the x-coordinate, and then we have the y-coordinate, and then the first, second, and third derivative values. So what we notice here is that when the polynomial derivative is non-zero, or not identically equal to 0, and we're talking about the higher derivatives, not just the first one, we have that the function derivative at 0 equals the polynomial derivative at 0. And what must be true about the power series, which is an infinite polynomial p of x, and the function f of x if they are to be equal? Well, we have that the cubic polynomial, for example, is equal to the function f up until the third derivative, but beyond that they don't match. But in order for an infinite polynomial, which is not what we had with m of x, to be the same as f of x, we need that f of n at the center, which in general we could call it a, but we will say 0 for now, for n greater than or equal to 0. Here what we had from the table was this was true for n contained from 0 to 3. And so this is leading us one step closer to how we get a power series that can be matched to a function if we cannot see it as an algebraic composition, a product of another function, or the derivative or an antiderivative of a known basic series. What we have then is the idea to construct a fourth degree polynomial matching the derivative behavior of f of x up to and including the fourth derivative. So we are going to let a polynomial, I'm going to refer to it as t subscript 4, because it's a fourth degree polynomial that is going to be tailored to this f of x function. And we're going to see Taylor polynomials and Taylor series shortly. And since it's a fourth degree polynomial centered around x equal to 0, it has this form. Now this is just going to be like question number 6, except in this case we are not given the information of what p0, p prime of 0, etc. must be in order to solve for the 5 unknowns. But we do know that p of 0 has to equal f of 0, and we know that p prime of 0 has to equal f prime of 0, and we know that p double prime of 0 must equal f double prime of 0, or t4 instead of p. p triple prime of 0 is equal to the third derivative of f at 0, and also for the fourth derivative. And so we have to actually calculate the derivative values, the 0th, first, second, third, and fourth derivatives, so that we have our 5 equations to solve for our 5 unknowns. So the first thing we're going to do is calculate f of 0, f prime of 0, f double prime of 0, etc. And I'll let you do that. I'll get you started with the first one, show you how to work this out. F of x is equal to ln of 1 plus x, which implies that f of 0 is equal to the ln of 1, which is equal to 0. I recommend working down in a column, work out f prime of x, and then evaluate f prime of 0. Then work out f double prime of x and evaluate f double prime of 0. I'm going to stop the video. You get these calculations for yourself, and if you feel ready, go ahead and solve for the coefficients c0 through c4. Now that we have all of the derivatives of f from the 0th to the 4th evaluated at the center x equal to 0, we know that that's what p of 0, p prime of 0, etc. must be equal to. And so now we have an equation that allows us to solve for our coefficients. And so when we do this, we can maybe recognize directly that p of 0 is only going to be c0, and so solving without writing much work down, we get that c0 is equal to 0. P prime is going to be c1 plus terms involving x, and so p prime evaluated at 0 is going to be c1 plus terms involving 0, or plus 0, and so p prime is equal to c1. And as a result, c1 must equal to 1. When we take the second derivative of the polynomial, we're going to get 2 times 1 times c2 times 0 times 1, and then these two terms will still involve x, so that when we substitute 0 in for them, we're going to get 0 from this term, 0 from this term, but we are going to get 2 times 1 times c2, which is 2c2, and that will be equal to negative 1. And as a result, we solve for c2 equal to negative 1/2. The third derivative, this term is going to be the constant term when we take the third derivative, and the third derivative will be 3 times 2 times 1 c3 times x to the 0. In other words, it will be 3 factorial times c3. And then this term will still involve an x, so that when we substitute the 0 into the polynomial, that term does not contribute, and we have that 3 factorial c3 will be equal to 2. In other words, c3 will equal 2 divided by 3 factorial. And lastly, the fourth derivative will come from the last term of the quartic polynomial. We'll get 4 factorial times c4 is equal to negative 6, and therefore c4 is equal to negative 6 over 4 factorial. And we can certainly generalize this. We're going to get that this is the value 0, which was the 0th derivative of f, divided by 0 factorial, which is 1. And this is the 1 coming from the f prime, divided by 1 factorial. And if we generalize this a little bit more, we need some more room. I'm going to copy that. We can generalize this, and we can see that there is more to this story, because this 0 number came from f of 0, and then it was divided by 0 factorial. And then this 1 value came from f prime of 0. So this is f prime of 0 divided by 1 factorial. Okay, I'm going to make this a little bit bigger. C2 came from negative 1 divided by 2, but negative 1 was the second derivative of f. So we have f double prime of 0 divided by 2 factorial, and sure enough, this 2 came from the third derivative, and negative 6 came from the fourth derivative. So we have the third derivative of 0 divided by 3 factorial, and we have the fourth derivative of 0 divided by 4 factorial. Moving on to number 9, we have a Pn polynomial, or a Tn polynomial, we may be calling it later on. We want to know, centered at x equal to a, which is the first identically zero derivative. If we have an nth degree polynomial, then the first derivative to be 0 is the n plus first derivative. And the derivative that is a constant function is the one before the 0th derivative, which is the nth derivative. Only the last term, the highest degree or the nth degree term, will survive, and the higher order derivatives in the patterning tells us that the derivative is going to be n times n minus 1 times n minus 2 times dot 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 times 4 times 3 times 2 times 1. And when this 1 comes down, we know that we still have a cn there, but we know that the exponent on x minus a is 0, which is why we have a constant as far as x is concerned. And so in other words, the nth derivative is going to be n factorial times cn. In number 10, we're going to take an infinitely differentiable function, and we're going to let it have a power series given by p of x, which is expressed with coefficients and powers of x minus a. So how many times can the derivative of the polynomial be determined? Since it's an infinitely long or infinitely high degree polynomial, we have infinitely many times. So both the function and the polynomial can have the derivative taken infinitely many times. In part B, we want to let p have the same derivative behavior as f at the center. So what we mean is that every derivative of f at a must equal every derivative of the polynomial at a, which allows us to come up with an infinite number of equations to solve for the infinite number of coefficients. In part C, we want to determine Pn, the nth polynomial of x, and we want to evaluate the nth derivative, rather, not the nth polynomial, the nth derivative of p at a, and then solve for Cn. Well, we know that p of x is going to equal c0 plus c1 x minus a plus c2 x minus a all squared plus dot 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 plus cn times x minus a to the n plus cn plus 1 times x minus a to the n plus 1 plus dot dot dot. And therefore, the nth derivative of p is going to have all of these terms going to 0, and then the first term that will survive is the nth term, which we saw its derivative is n factorial times cn times x minus a to the 0. And then we're going to get plus other terms here. In fact, I'm not really interested in those other terms, so I don't really want to know the nth derivative of p. What I'm looking for, so this should be the other terms are in x minus a. What I'm really looking for is the nth derivative of the polynomial at x equal to a. And since the other terms involve x minus a, every time I substitute in a, they will all go to 0 when x is equal to a. And so all I will be left with is the constant term. So n factorial cn. In part D, we want to write f of x as an infinite power series in both sigma notation and expanded form. So f of x is going to equal p of x. It's going to equal c0 plus c1 times x minus a plus c2 times x minus a. But each time the c1, the c2, etc. will be solved for. The coefficients we know have to be written in terms of, if we go back and we solve for Cn, of course, we didn't finish this one. Solving for Cn, we set this equal to this, and then we can solve this equation for Cn. And it says that Cn is going to be the nth derivative of f at a divided by n factorial. So we're going to use this essentially as a formula for each of the coefficients of the polynomial. So let's go back and fix this, knowing that we are going to expand f of x with c0, c1, c2, etc. We have that f of x is going to be the sum from n equals 0 to infinity of the Cn, which is the nth derivative of f at the center a, divided by n factorial times x minus a to the exponent n. So from here, let's just remind ourselves over the page that Cn is equal to the nth derivative of f at a over n factorial. And so when we expand the sigma notation, we get the 0th derivative of f is just f. So f of a divided by 0 factorial times stuff to the 0 is 1. Plus f prime of a divided by 1 factorial, we don't really need the 1 factorial, times x minus a to the 1. Plus f double prime of a divided by 2 factorial, which is just 2, times x minus a squared. Plus f double prime of a divided by 3 factorial times x minus a cubed. Plus, we'll do one more, the 4th derivative of f at a divided by the 4 factorial times x minus a to the 4 plus dot dot dot. Is p of x a geometric series? Well, in order to be a geometric series, C naught has to equal C1, which is equal to all Cn, etc., for a geometric series, to be a geometric series. So in general, no. However, it is possible that f of a equals f prime of a equals f double prime of a over 2 equals f triple prime of a over 3 factorial, etc. What it would require is that the nth derivative of a is equal to n factorial, for example. So in general, we'll just say no. What limitations are there in expressing f of x as p of x? Well, recall, p of x is a power series. And f of x is the sum of that power series. So we can only say f of x is equal to p of x when the power series converges. And the power series will only converge on the interval of convergence. So therefore, f of x equals p of x only on the interval of convergence. We are now ready to define the Taylor series for a function f of x, which can be horizontally translated or centered about any x coordinate, called x equal to a, as a special kind of power series, or infinite polynomial, in terms of the powers of x minus a, so the base of the exponents are x minus a, and we want the Taylor series, which we can call t of x, to have the same derivative values as x equal to a, at x equal to a as the function f of x. So our condition is that the n derivatives of f at a are equal to the n derivatives of t at a, and this is true, which implies that the coefficients are given by the nth derivatives of f at a divided by n factorial. So then we can see that the general case of the Taylor series can be written as a power series where the coefficients Cn have been substituted. And of course, this is only true on a specified interval of convergence. We could expand the Taylor series as the expression above. There are a couple of special cases of Taylor series that are important to know. In particular, we already know the linear approximation, or the equation of the tangent line, is the first degree, or the first order Taylor series. So we would call this linearization would be the Taylor polynomial of degree 1. So we call this the first degree Taylor polynomial. And the quadratic approximation is the second degree Taylor polynomial. So we call the Taylor polynomial the approximation because it has been the infinite power series or Taylor series chopped off. And furthermore, T2 is equal to the quadratic approximation from Cal 1, which is the second degree Taylor polynomial. So the Taylor polynomial is of finite degree, finite number of terms, and it is an approximation to the Taylor series or the power series, which is an infinite polynomial. We have a third special case, which is called the Maclaurin series. It is a Taylor series, not a polynomial, so it's an infinite polynomial, but we are centering specifically at x equal to 0, so we are centering around the y-axis. So we haven't translated horizontally to the right or to the left. Okay, so let's take a look at some practical examples, but first we need to construct a library of basic Taylor series. And in this particular case, we are going to take the center to be a equal to 0, and so we are coming up with some Maclaurin series to no cold. We have already seen that for the function 1 over 1 minus x, which has the form a divided by 1 minus r, that we have the basic geometric series, 1 plus x squared, etc. In this case, because the coefficients are all 1, we know that we have a geometric series, but furthermore, the coefficients, numbers 1, 1, 1, 1, are also going to be of the form of the nth derivative at 0 divided by n factorial. And so you could just evaluate some of the different derivatives for the function 1 over 1 minus x, which this is the f of x function on the left, and working them out, you will see that the derivatives keep working out to be the same as the n factorial, which is why the derivative divided by n factorial keeps working out to be 1. So we have the interval of convergence that r must be between -1 and 1, and we can write the summation notation. This is the version that we want to have when we express the Taylor series. We want the summation notation. However, it may be helpful and practical to expand out the series so that you can see the pattern and the expressions for some practical numbers. If we do an algebraic substitution with x being equal to -x, we still have a geometric series. We have the same interval of convergence because solving -x between -1 to 1 doesn't change, and we have an alternating series similar to the one before. The e to the x series is the sum of terms from n equals 0 to infinity of x to the n over n factorial, and happens to have a radius of convergence of infinity, which means the interval of convergence is all reals. We notice that for sine and cosine, these are functions with some symmetry. The sine function has odd symmetry, and only odd powers of x show up in the Taylor series. And we have this patterning for the nth general term, and we have the summation notation. Also, we have the interval of convergence is all reals for sine x and cosine x. The symmetry of cosine x is even, which is why only even powers of x show up, and we have the general term written over here. Ln of 1 plus x, we can see, is the antiderivative of b, and so we should remember that we can always generate power series by algebraic compositions of more basic power series, or by integrating or differentiating other basic power series. So if we were to take the antiderivative of b, we would get f. And if we take a look at term by term, the antiderivative of 1 with respect to x is x. The antiderivative of -x is -x squared over 2. The antiderivative of x squared is positive x cubed over 3. And the antiderivative of x to the n is x to the n plus 1 over n plus 1. But what we've done to change that is we've changed the index. So in fact here we have this n is the same as n plus 1 down here because we've changed the index. So we can see that there are two ways to get this series. We could work out the coefficients, the nth derivative of the function ln of 1 plus x, evaluated at 0 divided by n factorial, or we could take the geometric power series and Taylor series in part B, and we can antidifferentiate or integrate term by term. So I will just leave that as a connection, and you can fill in, because I don't have enough room here, to write antiderivative. Tan inverse of x has the Taylor series of x minus x cubed over 3 plus x to the 5 over 5, etc., which is also only odd powers. And if we recall, the graph of tan inverse of x is also an inverse function. it's also an odd function. It has odd symmetry, and as a result, only odd powers of x will survive once we have the Taylor series expansion. What that means is the nth derivatives when n is an even number will be 0, and that's why there are no even powers of x in the expansion. Do note that for the interval of convergence of ln of 1 plus x, we have from negative 1 to 1, but we are including 1 because we test at the endpoints. And similarly, for tan inverse of x, we have x contained from negative 1 to 1 inclusive. Moving on to number 11, we want to determine the Taylor series centered about 0. In other words, we want the Maclaurin series for each function above. If we were to work out the Taylor series for ln of 1 plus x, we could work out all of the derivatives for f and evaluate them at x equal to 0, and then come up with a pattern. However, it is a more efficient approach to recognize the antiderivative behavior of 1 over 1 plus x to give us ln of 1 plus x. And so we would start with a simpler Taylor series 1 minus x plus x squared plus dot dot dot, and integrate term by term to get the Taylor series for ln of 1 plus x. Let's rather take a look at sine of x and come up with its Taylor series from scratch. So we start off by writing the function, let f of x equal sine of x, and then we work out some derivatives. And our goal is to find a pattern in the derivatives so that we can generalize to the nth derivative and therefore the nth coefficient. So we do know that there is a cyclical pattern for the derivatives of sine and cosine of x. And it's a pattern that repeats after 4 derivatives. And so we know that f at 0 will be 0, f prime of 0 is positive 1, f double prime of 0 is 0, f triple prime of 0 is negative 1, and the fourth derivative of 0 takes us back to the beginning of the cycle, which is 0. Combining this with the fact that we know that the nth coefficient is the nth derivative of f at 0 divided by n factorial, and therefore the Taylor series is given by the sum from n equals 0 to infinity of the nth derivative of 0 divided by n factorial times x minus 0 to the n. We're going to come up with the Taylor series in expanded form and then write the nth general term. So we know that f of x is going to be the first coefficient, rather the first derivative value, 0 divided by 0 factorial. Let's actually just expand it a little bit like this. So the 0th value of f at 0 plus f prime of 0 divided by 1 times x plus the second derivative at 0 divided by 2 factorial times x squared plus the third derivative of f at 0 divided by 3 factorial times x cubed plus dot dot dot. So once we expand it, we can start to plug things in. We have the 0th derivative, or the height of the function, is 0, plus 1 times x, plus 0 over 2 times x squared, minus 1 over 3 factorial x cubed, plus 0 over 4 factorial times x to the 4, minus, we're back to the beginning, so we're actually at plus 1 over 5 factorial x to the 5, plus 0 over 6 factorial times x to the 6, minus 1 over 7 factorial x to the 7, plus dot dot dot. So what we want to do before coming up with a pattern here is rewrite the non-zero terms. And so we have x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus dot dot dot. And now we can start looking at a new index system. Here we had n equals 0, n equals 1, n equals 2, n equals 3, etc. Well, now I'm going to take a look at this being k equals maybe 1 or 0, I'm going to use a different letter, a different index, k. And then I can rename k back in terms of n if I like. So I see here that the exponent and the number for the factorial is changing each time, and so I need an expression that will represent that. And so if k is equal to 1, then I'm going to get, well, let k equal to 0 here, k equal to 1, k equal to 2, etc. Then my nth general term is alternating, so I'm going to have -1 to some exponent. I'm going to have x to some exponent and divided by something factorial. So each time I have k equals 0, 1, 2, 3, the changing number is 2 times k plus 1. So I have 2k plus 1 for the exponent on x and the factorial. But I also have alternating, and I have positive terms when k is even and negative terms when k is odd, so I just want -1 to the k. So that would give me a sum from k equals 0 to infinity of -1 to the k times x to the 2k plus 1, ensuring that I have an odd degree power series and therefore an odd symmetry function, divided by 2k plus 1 factorial. Now if I wanted to, I could go back and write that in terms of n, but what we have to be clear about is the n that I'm using in red is not the same n that I was using in the beginning. And I'm going to change all of these colors to black. And the reason for that is because I don't want you to think that this n in black and this n in red is the same n. Because we had n equals 0, 1, 2, but when n was equal to 2, that's k equal to 1. And so now I'm just going to write it back in terms of n because everything has always been written in terms of n. And the last thing we need to do is work out the interval of convergence. So if we want to work out the interval or radius of convergence, we use the ratio test. So L is equal to the limit, as n approaches infinity, of the absolute value of the an plus 1 term divided by an. And so the an plus 1 term is what we get when we take the general term, this is an here in red, and we substitute n with n plus 1. So let's just write an off to the side here. Is -1 to the n times x to the 2n plus 1 divided by 2n plus 1 factorial. And we'll do it very carefully. We get the absolute value, so this -1 to the n will not be involved. We will have x to the 2 times n plus 1 divided by 2 times n plus 1 factorial times the reciprocal 2n plus 1 factorial over x to the exponent 2n plus 1. So we can simplify the exponents. And here we're going to get 2n plus 2 plus 1 is going to be 2n plus 3, and so will this be 2n plus 3. So if we expand this, we're going to get x to the 2n plus 1 times x squared divided by 2n plus 3 times 2n plus 2 times 2n plus 1 factorial multiplied by 2n plus 1 factorial over x to the 2n plus 1. And we can reduce x to the 2n plus 1 top and bottom. We can reduce 2n plus 1 factorial top and bottom, and we can take the absolute value of x squared in front of the limit, whose variable is n, and we are left with 1 over, we don't need absolute value since n is positive, or at least non-negative. And furthermore, we don't need absolute values around the x squared because x squared is a non-negative expression, and we see that we get x squared multiplied by the value of this limit. And this limit really has 0n squared plus 1, so we have 0n squared over 4n squared is the end behavior, which is 0. So the value of the limit is identical to 0. No matter what value x is, the entire limit value, which is the limit of the ratio as the terms approach infinity. So it's like a common ratio, even though the early terms do not have a common ratio. And that limit value is identically equal to 0. So that means x can be anything, and the limit will be 0, which is going to be less than 1 for all x. And as a result, we see that the interval of convergence is x contained in the reals. And furthermore, the radius of convergence, if we were interested, is equal to infinity. The same process can be repeated for all of the basic series, for Maclaurin series. However, once we've done it for one, we can memorize the results and use these as basic series without proof or calculation. Moving on to number 12, we want to come up with a 6th degree Taylor or Maclaurin polynomial. So we know automatically that the center is a equal to 0. And the fact that we're coming up with a polynomial means that we are coming up with a Taylor polynomial of degree 6 or a Maclaurin polynomial of degree 6. If you want, you could still call it p subscript 6 of x. But this is an approximation like the nth partial sum of a series. And so what we need to do now is construct the various derivatives for f of x as well as their values at a equal to 0. So f of x is equal to 1 plus x to the exponent 1/2. We can work out f prime all the way down to f, the 6th derivative. And we can evaluate those derivatives at x equal to 0. I'm going to pause the video, calculate these myself. You do the same thing, and we can check to see how we got on after you unpause the video. 6 derivatives plus the original function value at x equal to 0. We can use these in the formula to calculate the coefficients of the Taylor polynomial, namely that Cn is the nth derivative of f at 0 divided by n factorial. And then we can multiply these by powers of x minus 0, or simply powers of x. So let's just write out a few terms. We have that f of x will be approximated by the 6th degree Taylor polynomial, or Maclaurin polynomial. And we have f of 0 plus f prime of 0 times x plus f double prime of 0 divided by 2 times x squared plus etc. And again, I'm going to finish writing this and then fill in all the terms and pause the video so you can try it on your own and see how you got on. The 6th degree Taylor polynomial centered about x equal to 6. As I was going through, I noticed I had a typo in my f triple prime value. I had 3 over 4, so make sure that that's changed to 3 over 8 from 2 times 2 times 2. And we could easily see the linear approximation as 1 plus 1/2 x, or the quadratic approximation as 1 plus 1/2 x, the linear approximation, minus 1/8 x squared. And so these are review from Cal 1. In number 13, we want to determine a Taylor series for f of x equals sine squared x, centered about x equal to pi by 2. We're going to change this from Taylor series to Taylor polynomial of, let's say, 6th degree to get more practice. And the patterning for this one is something that requires a little more extensive patterning than what we have for the basic. So we are just going to use, come up with another approximation, the 6th degree Taylor polynomial centered about x equal to pi by 2. I'll leave that to try, and you can check the answers later on. In number 14, we are given f prime of x equal to f of x over 1 plus x squared, and we know that f of 0 is equal to pi. In part A, we want to express f prime of x as a power series. We are told power series here, as opposed to specifically Taylor series, which means we won't have to do the patterning. The power series suggests we might try to find some other approach, namely, can we see this as a over 1 minus r with an a value different from 1 and an r value different from x. If we can, then we can use a composition or some kind of multiple of this power series, which is also geometric, and also the Taylor series, for 1 over 1 minus x? Well, in fact, we can write f prime of x as 4x times 1 over 1 minus negative x squared. So we can see that a is equal to 4x, and we can see that r is equal to negative x squared. So if we take our basic series, 1 over 1 minus x, and we substitute a with 4x, and we replace x with negative x, we get the Taylor series to be 4x times 1 plus negative x squared plus negative x squared to the exponent 2 plus negative x squared to the exponent 3 plus dot 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 plus negative x squared to the exponent n for the nth general term plus dot dot dot. And so here we get 4x times 1 minus x squared plus x to the 4 minus x to the 6 plus dot 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 plus, and we want to separate the negative 1 from the x squared, so we get plus negative 1 to the n times x to the 2n plus dot dot dot. And now distributing the 4x through, we get 4x minus 4x cubed plus 4x to the 5 minus 4x to the 7 plus dot 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 plus negative 1 to the n times 4 times x to the 2n plus 1 plus dot dot dot. And once we have the nth general term, we are able to come up with the sigma notation. The nth term, and we can write the summation notation as negative 1 to the n times 4x to the 2n plus 1. When n goes from 0, we have the first exponent is 1, so x to the 1, multiplied by 4, multiplied by positive 1. So starting at n equals 0 to infinity. We also always need, like we think of functions, we come up with a domain. When we talk about power series, we must think about the interval of convergence. And since f prime is an algebraic composition of 1 over 1 minus x, we simply need to consider that r, which is negative x squared, must be contained between negative 1 and 1. So when we solve this inequality, negative 1 less than negative x squared less than 1, we can think of solving graphically. And in solving graphically, we find such a solution. We see that the graph of negative x squared lies between these two horizontal lines when x is between negative 1 and 1, and we don't want negative x squared to touch the red or the green line, so we do not want to include the intersection points, so we do not include the endpoints of the interval. And so we have that the interval of convergence is x contained from negative 1 to 1. Please make sure that you don't just incorrectly apply some algebra to the inequality. It is not valid, it is not legal, and the square root of negative 1 is not real, let alone equal to negative 1. The fact that they look alike is just a coincidence. So then in part B, the question asks to express f of x as a power series. Well, once we have the power series for f prime, we can integrate term by term to get the power series for f of x. So we take the summation notation for f prime, and we integrate with respect to x. Now, of course, when we integrate, we are going to get a constant of integration. And so our constant of integration, I will call it c. We are going to get the sum from n equals 0 to infinity of negative 1 to the n times 4 times x to the 2n plus 1, which is 2n plus 2, and we divide by the new exponent. There's a 2 common here, so we can reduce that with the 4. And that will leave us with n plus 1 in the denominator. And so from here we need to solve for c, just like in Cal 1 when we worked out the antiderivative by taking the derivative, by integrating, and we had f of x equals c plus something. We would substitute in for x and y and solve for the constant. It so happens that we are given an initial condition when x is equal to 0, y is equal to pi. So we substitute pi in for y, and we substitute 0 in for x, which makes the entire expression in the summation 0. And as a result, we can solve that pi is equal to c. Obviously, if x hadn't been equal to 0, then the summation would be non-zero and it would be harder to solve, but we are not looking at cases like that because that's the whole idea of evaluating an infinite series by using approximations and estimating the error. It is a bigger problem than simply substituting in a term that will make the series 0. And so as a result, we have that f of x is equal to pi plus the sum from n equals 0 to infinity of negative 1 to the n times 4 times x to the 2n plus 2, all divided by n plus 1. And the last thing we want to note is the interval of convergence, which, since we have the antiderivative of a previous series, we have the same interval of convergence, negative 1 to 1. We should really clarify here what gets preserved is the radius of convergence. We always, always, always need to test at the endpoints. So we will test at x equal to negative 1, and we will test at x equal to 1. Substituting negative 1 in for x, we see that we get negative 1 to the 2n plus 1, which, if we rewrite 2n plus 2, that's going to be x to the 2 multiplied by n plus 1, which is the same as x to the n plus 1, and that quantity all squared. So we're going to have negative 1 substituted in for x, and then we're going to have to some exponent, which is either positive 1 or negative 1, but then squared will make the result positive 1. The same thing will happen when we have x equal to 1, that this whole result will equal to 1. So whether x is equal to negative 1 or positive 1, this quantity of x to the 2n plus 1 will always be positive 1. So we can actually test the two endpoints at the same time. So we have that f of plus or minus 1 is equal to pi plus the series from the sum from n equals 0 to infinity of negative 1 to the n times 4 times plus or minus 1 squared, which is going to be plus or minus 1, divided by n plus 1, which is pi plus 4 times the sum from n equals 0 to infinity of negative 1 to the n over n plus 1. And if we want to explore the convergence of this, we can see it is no longer a power series, as x does not show up in the summation. And we notice that it has the same end behavior as the alternating harmonic series, so it will have the same convergence behavior as the alternating harmonic series. So if we took a look at the alternating harmonic series, this series converges by Leibniz theorem, or the alternating series test. I should put converges in here. And therefore, since the limit as n approaches infinity of our term of our sequence term is equal to 1, we have, by the limit comparison test, this series converges, therefore f of plus or minus 1 converges, which tells us that we include x equal to positive 1 or negative 1 in the interval of convergence. So the radius of convergence will be the same, but we do always have to test at the endpoints for the series. In number 15, we want to use series to evaluate the following limits. When we substitute initially x equal to 0, we end up getting 0 divided by 0, which is indeterminate. And so we can use the series as an approximation for the sine 2x by replacing a transcendental function, something that involves exponential, logarithmic, trig, or inverse trig functions. We can replace it by an infinite polynomial. So we will get x squared times, and we have to know our memorized Maclaurin series for sine, and substitute x with 2x. So we will have 2x minus 2x in brackets cubed over 3 factorial plus 2x in brackets to the exponent 5 over 5 factorial minus dot dot dot, then minus 2/3 x cubed plus 4x, all divided by 9x minus x to the 5, and I'm going to factor out an x and reduce with one of the x's factored outside here, one of the x's here, and one of the x's here. And so what we see when we substitute x equal to 0, at this stage, we're going to get x times this infinite polynomial is going to give us 0, because all of these dot dot dots refer to terms that all involve higher powers of x. And then we have an x squared term, and then we have a constant once we divide out an x. And as a result, we can see that substituting x equal to 0 will make all of these terms, this term and this term, 0, and the final result will equal 4 over 9. I'll leave part B for you to try on your own, in a similar way, replacing e to the negative x with its own Maclaurin series, namely the Maclaurin series for e to the x with x replaced with negative x. And then you can do that substitution with a few terms expanded plus dot dot dot, and you can see what simplifies and what the result will be from this initially indeterminate limit. In number 16, we want to consider the indefinite integral of e to the negative x squared dx. We saw in Calc 1 that this is an integral that does not have a closed form, in other words, no other representation to evaluate or to determine this limit. This is like when we see a number like the square root of 9, which can be simplified to 3, but the square root of 10 cannot be simplified exactly to anything other than the square root of 10. We could approximate it to 3 point something, but we cannot express it in a different form without the square root sign. Similarly, we can't express the antiderivative exactly in any other form except the square root, the integral sign, except we now can in terms of an infinite series. So we want to use series to determine a power series for this function. So the first thing we're going to do is work out the Maclaurin series for e to the negative x squared, and we will start with the Maclaurin series for e to the x. So we have x to the n over n factorial as the nth term, and therefore e to the negative x squared is given as follows. We have an alternating series, and now what we want to do is integrate the series to get the antiderivative. So the antiderivative of e to the negative x squared dx is going to be the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n and then plus 1 divided by 2n plus 1 times n factorial. And then of course we have an indefinite integral, so we need plus c. It may be practical to expand this for a few terms, so what I'm going to do is look at the red term, the red series in expansion, which is going to give us 1 minus x squared. If we started off with this, it might be easier to see. And we have 1 minus x squared plus x to the 4 over 2 minus x to the 6 over 3 factorial plus x to the 8 over 4 factorial minus dot dot dot. And so our antiderivative would be the term-by-term integration of this. So we are going to have x to the 5 over 5 times 2, x to the 7 over 7 times 3 factorial, etc. And then, of course, we have plus c, which I'm going to put at the beginning. So the antiderivative is going to give me x minus x cubed over 3 times 1 factorial plus x to the 5 over 5 times 2 factorial. Let me just double check that. 2 factorial minus x to the 7 over 7 times 5, 3 factorial, etc. And what we have here is the general antiderivative function, capital F of x, if e to the negative x squared was little f of x. So when we want to work out the definite integral from 0 to any value, in this case 0 to 1, e to the negative x squared dx, we are going to substitute by the fundamental theorem of calculus the bounds, top bound and bottom bound, as follows into the antiderivative function. So this is going to give us c plus 1 minus 1 cubed over 3 plus 1 over 2 factorial minus 1 over 7 times 3 factorial, etc., minus c plus 0. So the c's subtract, leaving us only with the body of this antiderivative with x substituted with 1. So we have that the definite integral from 0 to 1 of e to the negative x squared dx is equal to 1 minus 1/3 plus, I can't remember them, 1 over 2 factorial minus 1 over 7 times 3 factorial plus 1 over 9 times 4 factorial minus 1 over 11 times 5 factorial plus dot dot dot. And of course, this is an exact value expressed as an infinite series, but we want to approximate it according to the instructions, accurate to within 2 decimal places, which means that the first digit that can change between the two values, exact and approximate, is the 3rd decimal place. And so we need to really find out how much of this can be the SN approximation for the S exact value. But we need to do it such that the error, which is not just the difference between the exact S and the approximate SN, but it's the magnitude or absolute value, which is the magnitude or absolute value of Rn, has to be less than 0. Or equal to 0.001. Well, we notice that the series is an alternating series that satisfies the conditions of the alternating series test. Bn is positive, so that the signs are always alternating. 2, it is a decreasing series, so Bn is strictly greater than the next term. And the third thing is that the nth term, this expression, is approaching 0 because we have n factorial, the biggest growing type of expression in the denominator. So we have the limit as n approaches infinity of Bn is equal to 0. And as a result, we can use the alternating series error estimation, which says that the Rn term is going to be less than or equal to the magnitude of the An plus 1 term. So what we really need to do is compare some fractions. Let's look at 0.001 as a fraction. We need this term to be less than 0.001 or equal to, which is 1 over 1,000. And we want the An plus 1 term in absolute value, without the plus or minus, to be less than that, which means we need the denominator of the An plus 1 term to be more than 1,000. So let's just work out some of these denominators. We have 2, and then we have, is there a problem here? Let's just look if I copied it down correctly. Yeah, I'm missing a 5 here, that's all. 5 times 2 factorial in this term. That's the problem, copying from one slide to the next. So if we work out some of the denominators, we get 3, we get 5 times 2, which is 10, we get 7 times 3 times 2, which is 42, we have 9 times 4 times 3 times 2, so 4 times 3 times 2 is 24, and 9 times 24 is 10 minus 1 times 24, so it's 240 minus 24, which is 216. So far we don't have a denominator that is bigger than 1,000. What about 11 times 5 factorial? So 11 times 5 factorial is going to be 11 times 5 times 4 times 3 times 2 times 1, which is 11 times 120. And so without actually working this number out, I know that it's going to be more than 10 times 100, because 11 is more than 10 and 120 is more than 100. And 10 times 100 is 1,000. So I know that this denominator is greater than 1,000. And that's all I needed to know. I needed to find the first term whose denominator was greater than 1,000, so that the reciprocal, or the term value itself, the magnitude, was less than 1,000. So that means that this term is less than 1 over 1,000, and that is my an plus 1 term. So it turns out that I'm going to use these terms for my Sn as my approximation to S, such that the error is within 0.001 of the exact value, or the approximation is within 0.001 of the exact value. So let's approximate accurate to within this, means we want to evaluate Sn for the first 1, 2, 3, 4, 5 terms. Therefore, Sn is going to, let me write, S is approximated by, and S is exactly equal to e to the negative 1 x squared dx integrated from 0 to 1 will be approximated by Sn, where Sn equals 1 minus 1/3 plus 1 over 5 times 2 factorial minus 1 over 7 times 3 factorial plus 1 over 9 times 4 factorial, which we said was 1 minus 1/3 plus 1/10 minus 1 over 42 plus 1 over 216. We'll leave it at this point, although we could get a common denominator and simplify this result as a rational number. In number 17, we want to determine the second degree Taylor polynomial for f of x equal to x squared plus 6x minus 8. Well, this is kind of a redundant or meaningless question because f of x is a second degree Taylor polynomial, and we can see that f of x can be written with a constant plus a coefficient times x minus 0 plus another coefficient times x minus 0 all squared. And so in fact, f of x is exactly the same as the second degree Taylor polynomial, which would be exactly the same as the Taylor series, which means the infinite polynomial. And so the Taylor series, let me just write here, I'll fit it in, is t2 of x, and the Taylor series is t of x. So this is the second degree polynomial approximation, where this is tx, t of x is the Taylor series. So if the Taylor series is an infinite polynomial, then the Taylor series is negative 8 plus 6x plus x squared plus 0x cubed plus 0x to the 4 plus 0x to the 5 plus dot dot dot. And we know this is true because for a second degree polynomial, the third derivative and every derivative after that will be 0. And so recall that these coefficients are the derivative at x equal to 0 divided by n factorial. And the nth derivative of f at 0 will be 0 when n is greater than or equal to 3. So we only have a quadratic polynomial. But if we wanted to center the polynomial at a different center, say a equal to negative 3, I just want to make a connection back to some algebra and pre-calculus. F of x squared is a f of x is a quadratic that can be transformed by completing the square. And so in part B, we have that f of x is equal to x squared plus 6x minus 8. And we can complete the square here. F of x x squared plus 6x plus 9 minus 9, and then minus 8 gives us x plus 3 all squared minus 17. So in fact, f of x is equal to negative 17 plus 0 times x plus 3 to the exponent 1 plus 1 times x plus 3 to the exponent 2. So when we complete the square, we could really see that we are translating the center, but this is still equivalent to the original negative 8 plus 6x plus x squared. So whether we center around x equals negative 3 or x equal to 0, we can come up with a different representation centered around a different x coordinate for the same function with the same Taylor polynomial approximation or with the same Taylor series. So the plus 3 meant that we were shifting 3 spaces to the left, and that was kind of easy. But how would we translate when we wanted the center to be x equal to 2, because we are not going to get completing the square giving us x minus 2? Well, I'm going to leave you to think about that from the point of view that what we are looking for is f of x equals some coefficient c0 plus a coefficient c1 times x minus 2 plus a coefficient c2 times x minus 2 squared. That has to be equal to negative 8 plus 6x plus x squared. And there are lots of different approaches. Just see if you can't come up with one. This is just an exercise designed to see you, to show you how the translations are related and how we kind of did a center translation when we dealt with completing the square. In number 18, we want to evaluate the following series. This is an example of the type of question where we're given something and we're good at going forwards, but we need to be equally good at going back. What we're generally given for the Maclaurin series and the Taylor series examples is the function, and we can create or generate the Taylor series. That's the going forwards. But we need to be also good at going backwards, given the series, identifying the function. This takes it one step further. We're not just identifying the function, but we're evaluating the function and the series at a specific x-coordinate. So we need to be able to recognize that we're given a Taylor series evaluated at some value c, and we need to recognize the function evaluated at c, which we can then calculate. So I will do one and leave you to try the remaining on your own. The first one, we have 1 minus 1/2 plus 1/3. And it's very hard to recognize what this series might look like if we don't know the basic series. So a quick look back to our basic series. And we should see from the expansion which series it reminds us most of. We don't have any denominators in the first two, so we don't expect A or B. We have factorials in the denominators for parts C, D, and E, so we don't expect that to be the case. And in F and G, we don't have factorials, but we do have some denominators, although for the tan inverse of x series, we only have odd numbers in the denominator. So it looks like ln of 1 plus x is the series that we are working with. So if we write the ln of 1 plus x, we can expand it as x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4 plus x to the 5 over 5, etc. And that suits us here as long as x is equal to 1. So this is equal to the ln of 1 plus 1. Now before we proceed, we had better make sure that this x value is in the interval of convergence. And when we recall the interval of convergence of ln of 1 plus x, we see that the left endpoint of -1 is not included, but the right endpoint of x equal to 1 is included. So we are allowed to substitute x equal to 1 into this series. So when we do that, we have that this series is equal to the ln of 1, which is equal to the ln of 1 plus 1, in other words, the ln of 2. And that is a sufficient final answer for this series. So in number 1, the exact value of the series is the ln of 2. Recognizing which series we have for parts B, C, and D, and then substituting the x-coordinate into the function and evaluating will give you the answers for B, C, and D. I'll pause the video, put the answers up, and you can check on your own. In part B, there was a typo. I was expecting 7 pi by 6 in the exponent, so I'm just going to change this denominator, but I have a note about what would happen if we didn't change the denominator. What we recognize here is we have an alternating series with a value plugged in for x or substituted for x to the n 2n plus 1 over 2n plus 1 factorial, so we should recognize the sine x series. Then, recognizing that dividing by 7/6 with the same exponent here means that we are multiplying by 6/7. However, I changed the denominator to 6/7, and so we are multiplying pi by 7/6. When we see that, our x value is 7 pi by 6, and the series is the series for sine. And we also must consider the interval of convergence, but x is contained in the reals for the sine series, and therefore this series is equivalent to, or converges to, the sine of 7 pi by 6, which is equal to negative times sine of the reference angle, pi by 6, which is negative 1/2. Had we not changed the denominator 7/6 to 6/7, the series would work out to be the sine of 6 pi by 7, which is not a special angle that we have memorized in the past, and therefore we cannot simplify further. So to work out exactly, we would leave the answer as sine of 6 pi by 7. In part C, when we recognize that we have only odd denominators with an alternating series, we recognize the inverse tangent series, which is convergent from -1 to 1 inclusive. So we see that the x value is 3 pi by 4, and we think that this is the tan inverse of 3 pi by 4. However, with x equal to 3 pi by 4, we see that that's a number which is bigger than 9 over 4, which is more than 1, and therefore 3 pi by 4 is not in the interval of convergence. Therefore, this particular series diverges, so the sum does not exist. So make sure that you are always checking that the x value satisfies the interval of convergence. So in this case, the answer is not tan inverse of 3 over 4, which would simplify, well, to a number that doesn't exist in this case, but tan inverse of 3 pi by 4 is not the answer for this series. In part D, we have -4 to the n, x to the n over 3 times n factorial. Rearranging this a little bit, we see the same exponent for -4 and x can be written as -4x all to the n, and then we have a constant of 1/3 which can be multiplied in front of the summation. Once we see this, we recognize that we have x to the n over n factorial as the basic nth term for the e to the x series. The interval of convergence is x contained in the reals, and so what we're doing is replacing or substituting x with -4x in the exponent, but we are also multiplying by 1/3. So here we are not getting a numerical answer, we are getting a function answer as the sum of the series, which is a valid expression no matter what x value we choose. So in this case, this is just another algebraic rearrangement of a basic series and not a value that we can calculate. Well, this concludes section 10.7, Taylor and Maclaurin series. Please make sure that you have completed the accompanying handout and prepared a list of clarifying lecture questions about the lecture. That's all for now.